Alright, in the last section we're going to talk about is mole conversions in stoichiometry. This is just showing how you can use the relationships between moles and grams, moles and liters, and moles and particles to relate the different quantities to one another. So key factors you do need to know, and these are ones I do expect you to be able to do without any assistance other than a periodic table, are your mole bridge, that 1 mole of any substance is equal to that substance's molar mass in grams, adding up the masses from the periodic table. That's based on Avogadro's number of units, and that's also equal to 22.4 liters for gases that are found at STP, 0 degrees Celsius, and 1 atmosphere pressure, or its equivalent. Units can typically refer to atoms, molecules, or formula units. We will see ions occasionally in AP Chem if we're dealing with something like F1 minus or Cu plus 2. If you're doing a percent composition calculation, it's just basically part over the whole. The grams of the element, or the part of the compound you're looking for, over the grams of the whole substance multiplied by 100. And again, for percentages, I do expect you just to round those to 1 decimal place. And then with stoichiometry, you're going to be using all the information from the mole bridge that we just discussed, along with coefficients, because you're going to be switching between substances, so you have to account for the ratios that are needed from the balanced equation to do calculations involving stoichiometry. So the first example we're going to look at is just a mole conversion. We know this is a mole conversion because it only involves CO2. I want to know how many liters are in 24 grams of carbon dioxide at STP. So I start with what I'm given, the 24 grams of CO2. I want to get rid of the grams, so they go in the denominator. And I want to find liters, so they go in the numerator. We said that 1 mole of any substance is equal to its molar mass, and so I would need to add up 1 carbon and 2 oxygens from the periodic table. You may round those to 2 decimal places, and when you do that you should get 44.01 grams. And then liters, we talked about when you are specifically at STP, will always be 22.4 for an ideal gas. So the grams are going to cancel out. When we look at this in terms of sig figs, the molar mass has 4 sig figs, the 22.4 has 3, and the 24 had 2. So we want 2 sig figs in our answer. So when we go through and do the math, you should get 12 liters. What's the percentage of nitrogen and magnesium nitrate, MgNO32? So we're looking at nitrogen specifically, and we want to know what it is in that whole compound. So if we're going to need to have masses, the only masses that we can probably get are from the molar mass of the periodic table. So I would take 1 magnesium, 24.31. I want 2 nitrogens because of the 2 in parentheses outside the NO3. So 2 times 14.01, and 6 oxygens, 6 times 16. And when I add those together, I get 148.33 grams. I want the part that's just nitrogen to be on top, so I need 2 nitrogens in the numerator, 28.02 grams. And I want the 148.33 to be in the denominator, because I want it over the whole compound. When I make that into a percentage, I multiply it by 100. The grams cancel out. Numerator, denominator, they're both the same, so that's why you don't see any units in a percentage other than just the percent sign. Again, I said we're going to round this to 1 decimal place, so that's why I said 18.9. And then the final example I'm going to do is a stoichiometry problem. You're given an equation right there. That's a good sign. It's going to involve stoichiometry. How many moles of silver sulfide, Ag2S, are made from 3.01 times 10 to the 23rd molecules of molecular sulfur, S8? So just like with our dimensional analysis, our mole conversion problems, we always start with what we're given, the 3.01 times 10 to the 23rd molecules of S8. Because we want to cancel out the molecules of S8, they need to go in the denominator. And because we want to find the moles of silver sulfide, they need to go in the numerator. Anytime we see moles, we want to use 1 as our default. Molecules, atoms, ions, formula units, we want to use Avogadro's number. Grams, we want to use molar mass. Liters, 22.4. But because these are not the same formula, and our ratio in our equation is not 1 to 1, we definitely want to make sure we include those coefficients. There's no coefficient in front of S8, so I just default to 1. There is a coefficient in front of Ag2S, so I use that 8. The molecules of S8 cancel out. I'm going to multiply across, And because these are ones here, you don't have to worry so much, but you got to make sure that you divide by everything in the denominator. Make sure you watch your parentheses so that you don't have your calculator muck up your answer. If you have put this in your calculator correctly, you should get 4.00 moles. I did 3 sig figs for this because our starting value had 3. Our coefficients do not count towards sig figs. They are exact quantities, as is the 1. And Avogadro's number can go out further, but this one had 3 sig figs, so that's why we're going to keep 3 in our answer. And this should help you be able to answer the final set of questions on your review assignment. 24 is all mole conversions, percent composition. 25 is a stoichiometry problem. Again, please remember with 25D, atoms, molecules, formula units, ions, they're all represented by Avogadro's number in terms of a mole. And if you have any questions, please don't hesitate to be in touch.